Hey everyone, in this video I want to talk about how to integrate powers of tangent and secant functions. To integrate powers of tangent and secant functions, we use some similar strategies that we saw for integrating powers of sine and cosine functions. For sine and cosine functions, we kind of remembered a few different strategies, while for secant and tangent functions, I think it's better to just dive right in and see what happens. When we have powers of tangent and secant that we are trying to integrate, there's one of two options that we are going to make for one of our substitutions. They're both going to be a u substitution, and we're going to either make a secant substitution or a tangent substitution. And instead of trying to remember a set of cases like are powers even, odd, positive, negative, things like that, I think it's better just to think about the differentials, try to plug some things in, and see if it works out. If it doesn't work out with your first try, well then you only have one other option. That usually ends up being more efficient than trying to read through all the different types of cases, identifying which case, and then getting started. So just like what we saw with powers of cosine and sine functions inside of our integrals, we're going to be able to make some initial substitutions using u and du that we see up here, but to kind of finish the rest of it off, to make the additional substitutions that may be needed, we're going to have to use one of our Pythagorean identities. It's not going to be the sine squared plus cosine squared equals 1, since we're not working with sine and cosine functions at the moment. Instead, it's going to be the tangent secant version of that Pythagorean identity that says tangent squared of theta plus 1 is always equal to secant squared of theta. So it doesn't really matter which one we try first here. I'm holding my pink pen, so let's go ahead and try a tangent substitution to begin with. And so we're going to see that this approach is going to fail for this example pretty quickly, because if we want to use a tangent substitution, we're going to need a spare factor of secant squared of theta. And so we might try to set up our integral to kind of prep it for this tangent substitution. So let's maybe pull out one of those factors of tangent from our tangent cubed. And so we're initially just rewriting this as tangent of theta times tangent squared of theta times secant of theta. And now our tangent of theta will become u, but we still have these extra factors of tangent squared and secant of theta that we have to take care of. And well, what we can see here is that in order to swap out our differential of theta in terms of our differential of u, we need an extra factor of secant squared. However, we only have a single factor of secant attached, so we don't have enough. Sure, we could rewrite tangent squared of theta as secant squared minus 1, and we would then have a secant squared showing up in our integral. However, it would not be a common factor between all the pieces inside of our integral, so we wouldn't be able to actually factor it out to make the rest of our u substitution work. So this approach with u equals tangent of theta will not work for this example. Well, then there's only one other approach to try, and that's making a secant substitution instead. So when we are setting our integral up for a secant substitution, in order to swap out our differentials, we're going to need an extra factor or a factor off to the side that is still a common factor of secant of theta and tangent of theta. So let's go ahead and set everything up. So we need one factor of tangent pulled out, so we can leave our tangent squared of theta out front. And then to get back to tangent cubed, we need that additional factor of tangent. Then we can't forget our factor of secant of theta and d theta as well. And now the idea is, if we are going to make a secant substitution, then the differential of u equals secant of theta du is this factor of secant of theta times tangent of theta times d theta. So that last product will turn into our differential of u, but now we still have this tangent squared of theta that we have to deal with. Remember, we're setting everything up for a u equals secant of theta substitution, and our tangent squared factor that is remaining doesn't have any secant of thetas when it's written in this form, but if we use our Pythagorean identity that says tangent squared of theta is equal to secant squared of theta minus 1, then we can make some more progress. So going from here to here, we've swapped out using our Pythagorean identity that tangent squared of theta is equal to secant squared of theta minus 1. The product of tangent of theta, secant of theta, and d theta became du, the differential of our new variable. And so now we can finish this substitution off, because what is secant squared minus 1 in terms of our new variable u? That's just going to be u squared minus 1. And so now our integral is written in terms of just u, so we can find its antiderivative. very quickly as well, just using our power rule. It's going to be 1/3 u cubed minus u plus some arbitrary constant of integration. Got to have that plus c. And so we have found the antiderivative of our intermediate function, but we're not done until we find the antiderivative of our original function, which is in terms of that original variable theta. So now all we have to do to finish this problem off is back substitute. Remember, this whole time we're using u is equal to secant of theta. So our antiderivative in terms of that original theta variable is going to look like 1/3 times secant cubed of theta minus secant of theta plus some constant c. And I think the key thing to remember when looking at these powers of tangent and secant integrals is really the first thing you're focusing on is swapping out the differentials. Right here we're able to swap out secant of theta times tangent of theta times d theta and turn that into just du, setting up our secant substitution. The idea is once you kind of visualize or actually write down swapping out these differentials, the pieces that should be left over should be just the u substitution piece you want to make, or should just be even powers of either tangent or secant. We need these even powers because these even powers allow us to use our Pythagorean identity to rewrite the current function in terms of the other function. And that's what we saw here, right? We had tangent squared of theta and we wanted to make a secant substitution inspired by our swapping of the differentials. But in order to make that secant substitution for tangent squared, we had to use this Pythagorean identity and rewrite tangent squared in terms of secant of theta or u.